Morning.
Good morning.
Quentin, you look a little tired.
Very tired. I didn't even get sleep well like that.
I understand a little bit. First, are there any questions or concerns?
No.
Go.
My lab 3 and 4, I emailed you about it, did not open back up for me. It's still saying I'm unable to do it. It like completely closed out on me.
Did you contact them? Did you
No, I did
contact
not
them?
contact them because it opens up for me now. It doesn't give me that like
You
error.
need it.
me out.
Miranda, I think this is Miranda. You have to contact them.
Okay.
I wish I could solve that, but I can't. You have unlimited attempts, so there's no reason for it to close on you. But I know that there can be there's settings with your computer that can change how it loads and whether or not it loads. And I don't know how to troubleshoot those. I call them and they troubleshoot it and fix it for me by telling me what to do. Let me know if it doesn't work, let me know that too. But call them first and let me know. Other issues?
So tomorrow the lab quest is due. Is lab exercise 5 due as well?
Yes.
Okay, thank you.
Other questions? You will see we are a little behind in lecture, and I'm worried, but I'm not worried. And part of it is because I think this is probably one of the more difficult chapters we have. I think it's the most difficult, if I remember right, overall. Bear with me. Getting my teaching assistant up here in my lap. In a minute, she'll just fall asleep in my lap throughout the rest of the class.
I do have a question. So
Go.
like I've noticed that when I try to do like whatever assignments are due, that I'm having struggle with keeping them like in order. Are they in chronological order? Because I'm noticing I'm doing homework that's like pertaining to other homework. Like it'll be like the one was like about the potassium bag. And they were like, what happens to the potassium bag? And I was like, I don't remember seeing a potassium bag in my assignment.
Are you referring to the chemist? Are you referring to a chemistry practice? No, those questions are not in order. No.
Okay. Nothing. Well,
No.
I mean,
they're
like,
randomized pool.
okay. So I'm not supposed to be doing like an assignment before I do another assignment for the second assignment.
I'm not sure exactly what you would have to tell me what the question actually said.
Okay.
Something about a potassium bag, and I can't specifically tell you about that one. Is this a lab question or is this a lecture question? Is it from McGraw-Hill or is it from Wiley?
I believe it was from Wiley.
All right, that's a lab question. And what exercise was it?
I'm not sure which one I was doing because I was just trying to catch up, and it seemed like I was trying to do everything in order. Like I wasn't trying to do lab 1 and 2B before 1 and 2A. I did it in order like A and then B.
I don't think that matters so much.
Okay.
But are you working on? I'm sorry, bear with me here. Are you working on? Was that exercise 5?
Maybe.
That would have to do with it because it had to do with diffusion. That's a different, that's what we covered last week in lab. We talked about osmosis.
I'm not sure. Maybe I don't remember specifically what the question was. I just remember that I looked at it and I was like, I feel like I should have did one of the other assignments before I did this assignment.
Well, if it had to do with a potassium bag, I would say that I would guess just from that statement alone that it had to do with the osmosis and the diffusion, which we covered last week in lab. We'll cover it again in lecture in about a week. But we covered it in lab last week. And things will start to get so they're more in order as the semester goes. But we do have to cover the basic chemistry before we cover other topics that build on that in the next chapter. Am I making it even more confusing?
No, I don't think so. I think I understand.
Okay. Other, Leo? No. Other questions, other issues? Okay.
No.
So I realize, yes, this first part of this chapter takes a really, it's very involved. It's very abstract concepts. But once we get to about the halfway point, which is around slide number 75, it gets a lot easier.
Really?
And the fact that I haven't lectured about on this material in about a year, I have to remember that it gets a lot easier and we'll start working through it a lot faster.
Good.
But just be patient with me as we go here. And let me know when you have questions, because
I do have a question.
go ahead.
So what is due specifically tonight? Because I know there's things
If you look, all your assignments are outside of the Wiley assignments.
Mhm.
I don't think there's anything due tonight.
Okay.
But if you look right here on the course home website,
Mhm.
with regards to McGraw-Hill, it tells you everything that's due
Okay.
here. I think with regards to Wiley, your lab 5 that we did last week is due tomorrow night.
Okay.
But all of the McGraw-Hill are their due dates are posted here. And I will, as we move through the material with regards to the McGraw-Hill lecture, this is the lecture material except for the lab quest here. Oh, the lab quest is also due tomorrow night, but it's right there on McGraw-Hill. So what's due tomorrow night? Lab exercise 5 and lab quest 1. Lab quest 1 covers exercises 1, 2, 3, and 4. And lab exercise 5 covered lab from last week. Does that help answer your question?
Yes. Thank you.
You're welcome, of course. So I'm going back a week. I will repost this in a moment. After class, I'll repost it, but I'm going back a week to finish chapter 19. I mean, chapter 2. Chapter 2. And we ended on slide number 56.
Are you sharing the slides?
Give me a moment. If you don't see it, I'll fix it here in a second here.
Okay.
I should have been sharing, I'm not sure. Are you seeing it now?
Yes.
Okay. So if you remember at the very beginning of chapter 2, we were talking about how there is a fluctuation of atoms that as the atoms rotate around the nucleus, there's a fluctuation and that we can't identify. There's a fluctuation in their orbits, and that we can't at any given moment pinpoint where the location of any given electron. They're too tiny and they move too fast. However, we know that within the shells, that is the average pathway that they tend to orbit in. So the result is that we draw them in orbits. I'm sorry, bear with me just for a second. You know what, I'm gonna wait. So they average, or they move around in the orbits, and they average, but on, excuse me, I lost my train of thought. If you look at an atom, they have a random cloud density, and they move around in that orbit, and the most common times that the most average, on average, where you will find them is within the shells. That's why we say that their most common pathways are in the shells. However, in reality, we know that because that's the most average, that doesn't mean that they can't be somewhere else within the area. They can't, here's the most common area, but on average, can they be out here? Might they be out here? Might they be out here? Yes. But they're most likely to be around here.
Between the face and the.
This also means that there can be random fluctuations in the density of the electrons.
Pick up, they won't work.
Be random fluctuations in the densities as they move around the nucleus. The result is that at times, this can render one side of the atom, here's the nucleus, here's the electrons in their cloud moving around. At times, that one side of the atom may be more positive and one side may be slightly more negative. If you remember, we talked about partial charges of polar molecules. This is the same thing, but it's around one atom. And these are random partial charges around a given atom. So the result is at times we can have a partial positive charge on one side and a partial negative charge on the other side at any given moment. And because we know the opposite charges attract, we can have different atoms more attracted to one another at any given moment. Any questions? These forces are important or protein folding, they're very weak forces. However, they're very important for protein folding, which we'll talk about in a few towards the end of this PowerPoint. They're very important for the binding of proteins one to each other, such as a receptor to a ligand or a hormone. They also are involved in interactions of lipid molecules within cell membranes, which we talked about a little bit last week during lab, but we'll talk about more in the next chapter. And a little bit in that as we go finish this chapter. So these are random fluctuations that result in a partial positive, partial negative charge across the atom and results in their attraction to one another. Now, I've got a question for you. What we've talked about 4 different types of bonds. What were they? This is one of them. What were the other 3?
One of them was a covalent bond.
One of them was a covalent. You're right. What else?
Wasn't one of them an ionic bond?
An ionic was another one. What else?
Hydrogen bond.
Correct, hydrogen. So we have covalent, we have ionic, and we have hydrogen, and we have this one, this van der Waals forces. Which one is the strongest?
The covalent bonds,
Why do you think it's the covalent bonds, Genesis?
because they're sharing electrons, so they're constantly pulling at each other.
Good job. Yes. The other 3, in an ionic, when we give one up completely to another atom, what we've done is we've just created a one atom that's got a negative charge and one that's got a positive charge. And their opposite charges attract, and that's the reason they stay together. And then the hydrogen bonds are created because of partial positive and partial negative charges, where the hydrogen has a partial positive charge and it's attracted to a partial negative charge on another polar molecule. And then we have this one where we have a partial positive and a partial negative charge across the atom. Now, so covalent bonds are the strongest. Which ones are the weakest?
The van der Waals forces. Is that how you say it?
Yep, that's how you say it, and you're right. The van der Waals forces are the weakest. So covalent are strongest, van der Waals are weakest. Right underneath the covalent, which one is the second most strongest? Is it ionic or hydrogen bonds?
Ionic.
Why do you're right. And then hydrogen bonds. So it goes covalent, ionic, hydrogen bonds, and van der Waals forces. So here, general idea. Covalent, a summary of them. Ionic, the weak attractions between an anion and a cation, easily disrupted in water as salt dissolves. Covalent, we can have single and double covalent bonds. Can have a non-polar covalent bond where things are equally shared, electrons are equally shared. Can have a polar covalent where they're not equally shared. Hydrogen bonds and van der Waals forces. Hydrogen bonds are similar to ionic bonds because of why?
Don't they both form molecules then?
Say it one more time.
Because they both form molecules?
Hydrogen bonds don't form molecules. It's
They
between,
both
it's
are due
between
to opposite
polar.
charge.
Say it one more time, Quentin.
I think it's A.
I
think
think you're right. I think it's A2. They hydrogen bonds don't form molecules because these are more like, let's refer to a hydrogen bond as being an interaction between two polar molecules. It's a good way to define that, and that it's working through the hydrogen bond. Or it's working through the hydrogen in another. So the hydrogen on one polar molecule is interacting with an electronegative atom on another polar molecule, and that's what's making a hydrogen bond. So water, 60 to 80% of the volume of most living cells is water. Water is very polar and it forms hydrogen bonds within itself. So a partial positive charge on hydrogen is attracted to a partial negative charge on another water molecule's oxygen, forming these hydrogen bonds. The water is very polar. We already said that. Depending on how other molecules interact with water, they are described as being hydrophilic, hydrophobic, amphiphilic, and amphipathic. What does it mean to be, what does the word hydro mean? If you see that as a base word, what does it mean?
Water.
It means water. What does philic mean?
Means like love of.
Love of, yes. So hydrophilic are other molecules that love water. They love water. Hydrophobic, what does phobic mean? What does it mean to have a phobia of something?
Scared of.
Yeah, you're afraid of or you're scared of. I mean, if you've ever, especially right now during the COVID mayhem, the people who are germaphobes are like, ew, 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 ew. That's hydrophobia, or what it means to be hydrophobic. So molecules that are polar are hydrophilic. Molecules that are non-polar, because polar will dissolve in polar. Water's polar. Anything else that is fairly polar will dissolve in water. Anything that has a charge on it will often dissolve in water. Or let's not even say often, will dissolve in water. hydrophobic, non-polar molecules. Amphiphilic or amphipathic are molecules that have a partial positive, have one part of the molecule is hydrophobic, one part of the molecule is hydrophilic. An example of an amphipathic or an amphiphilic molecule is a phospholipid, where the phosphate head is very polar. But the fatty acids, the lipid part of the phospholipid, is very nonpolar. These phospholipids are what make up the basis of the plasma membrane. And it's a two-layer formation where one layer is oriented so that all of the phosphate heads are located, are exposed to the water, and all of the fatty acids are inside. On the other side, the water, all of the other layer is oriented the same way. The result is that all of the fatty acids or all of the lipids are sequestered inside and not exposed to the water. And this process happens automatically. It's not something, it happens almost instantaneously. If you think about, I get a lot of rain in this area. It looks like we're going to get rain today, looking at the clouds outside just now. Initially, when it rains out on the road, well, there's always some oil out on the road. But initially, when it rains out on the road, within a matter of a few minutes or less, depending on how hard it rains, you'll start to see pools of oil, right? And it happens almost instantaneously because the oil is working to sequester, it is moving into a formation where it's least exposed to the water because it's hydrophobic. So the major reason we bring this up is so that you understand that molecules will interact based on whether they're hydrophobic or hydrophilic with regards to water. And if they're amphiphilic, they'll move around in a configuration where only the polar heads are the most exposed to the water. And the hydrophobic parts are least exposed. Any questions? Because water is very polar and it also hydrogen bonds with itself, it has a high heat capacity. This allows water to stabilize internal temperatures within the body. So this is why warm-bodied individuals like humans, warm-bodied organisms can survive even when it's really cold. Because it takes a lot of heat to raise the temperature of 1 gram of water 1 degree Celsius. It's a very high heat capacity. because of the hydrogen bonding and because of the polarity of water, it takes a lot of heat to add a certain amount of energy or a certain amount of, you have a certain amount of energy to water. It also has a very high heat of vaporization. This means that it requires a large amount of heat to raise, to, excuse me, to force water in a liquid state to enter a gaseous state. When, for example, you're on you're boiling water to cook some noodles of some sort, and after a few minutes, as long as you're not watching it, because a watch pot never really boils, you walk away, you come back, and it's got steam rising off it. The steam is individual water molecules they're condensing together a little bit, but individual water molecules that are breaking away from the liquid water because we've broken all the hydrogen bonds and allowed it to be released from the pool of water. Mom? Mom? Bear with me, guys, just a sec. So I have this bottle of water here. What holds it? Why doesn't it just immediately just start to vaporize?
There's no heat.
Say it again.
There's not heat applied to the water bottle.
Well, there's no heat, but even if there's a certain amount of heat in there, or it wouldn't move at all. When it comes, there's a certain amount of energy, like heat is just added energy. There's a certain amount of energy already in there. So why doesn't it just start to turn into a gas? I mean, there's a certain amount of energy to it. Me even moving it back and forward like this, I'm adding a little bit of energy to it by doing this. So why doesn't it just turn into a gas spontaneously? Because the individual hydrogen bonds between each water molecule are holding it together. The water molecules may be moving and breaking hydrogen bonds and reforming hydrogen bonds with other water molecules. And maybe every once in a while, one of them randomly escapes because it breaks all its hydrogen bonds and it's allowed to escape. But I've not added enough energy to it to allow for lots of water molecules to escape. But it's being held together by the hydrogen bonds in between the water molecules that are being, as I move it, they're being broken and reformed. If I turn it into ice, there's a lot less energy there, and the hydrogen bonds almost become more like crystalline structures, where they can't break and reform as easily. Let me give you another example. Dry ice. If you have you ever seen, you've ever gotten dry ice to like make homemade root beer or something? And you go and you pick it up, and the second you open even the incubator that it's in, or not the incubator so much as the, oh, what's the word for it? The refrigerator or freezer that it's in, you go, you open it, and it immediately starts becoming a gas. Even at room temperature, you don't have to add a lot of heat to it that isn't already there. And it immediately starts vaporizing. The difference between these two molecules. Let me also say this. Dry ice is frozen carbon dioxide. So the difference between these two molecules is CO2, or carbon dioxide, looks like this. My kindergarten looking like writing here. Looks like this. H2O, or water, looks like this. Sorry, that didn't work very well. Making that H. Water can hydrogen bond with itself or with other things. Carbon dioxide cannot. That's why carbon dioxide immediately starts to vaporize and escape into a gas with dry ice, and water does not. So even though hydrogen bonds are really quite weak, when there's a large number of them, they hold things together. And that's why water is very cohesive with itself. And carbon dioxide is somewhat cohesive, but the second you add any given amount of energy into it, it'll start becoming a gas almost immediately, spontaneously. Any questions? So water has a high heat of vaporization where it requires a lot of heat energy to change the water from a liquid to a gaseous state. Evaporation requires that the hydrogen bonds between the individual water molecules break to allow the liquid water to escape and become a gas. Evaporation also has a cooling effect on the environment and on the body. When you sweat, remember that's a homeostatic mechanism. That you start to get really hot, start to overheat a little bit. And your body recognizes that your body temperature is moving out, possibly moving towards levels where things are going to lose function and be beyond the narrow limits where we keep our temperature. And so your sweat glands start to secrete water onto the surface of your skin. That water absorbs a certain amount of heat from the body and then vaporizes. So when it absorbs the heat from the skin, it brings down in very minute levels. Overall, it's going to bring down the body temperature. Another thing about water is that because of its very polar properties, and also the fact that it hydrogen bonds, it's a universal solvent. Water forms hydration layers or around charged substances and around other other polar substances, producing biological colloids. If you think about ions, they're charged. Sodium here has a partial positive charge. When you put it in water, sodium chloride, you put it into water, the sodium with its positive charges orients the water in such a way, or the water orients itself in such a way that its partial negative charges are most attracted to the sodium ion, and the partial positive charges are directed outward. The chloride or the chloride ion is partially negative, or it's got a negative charge. So the partial positive charges of the hydrogens are what are oriented towards the negatively charged chlorine ion. These are what we call the hydration layers, allowing for these biological colloids, or colloids meaning that the substances in the water don't settle out with gravity. A solution is defined as a uniform mixture of two or more substances. The solvent is a dissolving agent like water. And the substance that is dissolved, like sodium chloride, is a solute. Also, water has, because of its properties and because of what it is, it's got a lot of reactivity associated with it. We can perform hydrolysis and dehydration reactions with it. I want to introduce a few terms here that aren't defined right here, but they're going to be defined later in the chapter. But I think they're important to understand here too. Let's see here. Oh, that's not what I meant to do. So a monomer are individual subunits. You think mono means one. Individual subunits. Or an individual, let's say a monomer is an individual subunit. Polymer is two or more monomers bound together. For me, sometimes it's easy because I have nieces and nephews who love Legos. And it's easy for me to think of monomers as being the individual Lego blocks. And that when you build up a tower or build up any kind of object using those Legos, you then got a polymer. Poly meaning more than one. A dehydration reaction is the removal of water in the formation of covalent bonds between monomers. Hydrolysis reactions are the addition of water, to break addition of water to break bonds between monomers. And I know that I am not a very fast typist, so I'm going to keep going knowing that I'm a very slow typer and that you probably have all that typed up. But we'll see that again also in a future slide here. So hydrolysis reactions add water to break up a polymer into the individual monomers. Dehydration reactions remove water to bind individual monomers together. A dimer meaning two. Water, as we saw with the charged ion of sodium chloride, are capable of adhering to charged substances and are also capable of being cohesive, meaning hydrogen bonding with itself. It also works as a cushioning effect. If you want to think of that cushioning effect, this bottle of water here, and I don't know if you saw that I drank some of this water a minute ago, so we're not going to actually drop something in it, but pretend that I drop a marble into there. It's really fast initially until it hits the surface of the water. And then what happens? Does it keep going that fast? Does the drop continue? Does it continue to drop as fast once it hits the water? Someone tell me.
Nope.
Nope, it doesn't. Because the water then cushions the fall of the marble. So that's the cushioning effect. Onto some simpler, for a few minutes here, some simpler ideas. Mixtures are substances of two or more components physically intermixed. We have three basic types. We have solutions that are homogeneous mixtures of components like gases, solids, and liquid, that can be gases, solids, or liquids. So homogeneous, equal across the mixture. We have colloids, which are heterogeneous mixtures, where the solutes are larger than those in true solutions, but they don't settle out with gravity. Nevertheless, the individual solute particles can scatter light. These colloids can also exhibit a solid-gel transformation, if you think, where you get a reversible transformation between a liquid to a solid. An example of this would be Jello. A cytosol of the cell is another one. Suspensions are heterogeneous mixtures with large, often visible solutes that tend to settle out. If you think, and I don't have any kids, but I have lots of pets. I've had lots of pets over the years. And when you go to a vet, they often will send you home with a medicine, and they tell you to shake that medicine before you use it, because that medicine is in a suspension, and you leave that bottle sitting for very long and the medicine will settle out to the bottom. So you have to shake it to get a reasonably homogeneous mixture before you take a sample out. I've also received medicines in the past that were in glycerol or in some sort of corn syrup. And when they're in some sort of corn syrup, they're colloids. They don't settle out. They don't need to be shaken. They also don't have to be refrigerated most times. There's differences between a mixture and a compound. Mixtures can have a variable composition. You can vary the amount of each substance in a mixture. A compound has a definite composition, and you can't vary the amount of each element in the compound. A mixture, the different substances are not chemically bound to one another. In a compound, the different elements are chemically bound to one another. In a mixture, each substance keeps its own individual properties. We don't change the chemical properties of each substance in a mix of a given mixture. A compound, because it's bound to the different elements, each substance is bound to the individual other substances within the compound. The properties are going to be different based on what elements are bound. Chemical properties. In a mixture, each substance is easily separated from the mixture. In a compound, the only way to separate the elements is to use chemical reactions and break the bonds. Some examples of mixtures are air, seawater, and most rocks. Examples of compounds are water, carbon dioxide, magnesium oxide, and sodium chloride. Water, and I meant to flip this slide around. I didn't mean to have it right here. Obviously, it didn't work very well. Water can ionize. If you remember, ionizing meaning forming ions with itself. The water one water molecule can take on a hydrogen molecule from another water molecule. And the result is that we get a positive charge here. And we leave a hydroxide ion. We'll add some more terms really quick to our list of terms here. Hydrogen ion is a hydrogen atom that has lost its electron. A hydronium ion is a water molecule. That takes a hydrogen ion from another water molecule. Water molecule. And what forms is a water molecule that has a plus charge on it because of the hydrogen ion it just took. A hydroxide ion is a molecule. It can form from two different ways. It can lose a positive. It can be the result of its ionized anything that. In this case, let's just refer to this case with water. A hydroxide ion is a water molecule that has lost hydrogen ion. We can form hydroxide ions from other things that lose positively charged ions or lose other cations. But in this case, in this slide, it's because we've lost a hydrogen ion. So water ionizes by giving up a hydrogen ion to another water molecule. And then that we form two different ions. This is not a stable ion. This is not a stable ion. This becomes an acid. An acid is defined as something that easily gives up a hydrogen ion. This is a base that easily accepts a hydrogen ion. So water ionization results in the formation of both an acid and a base. In pure water, in distilled pure water, the hydronium ion and the hydroxide ion concentrations are equal. Therefore, it has a neutral pH of 7. So acids and bases dissociate in water. When they dissociate, acids release protons. If you think, let me ask you, why would we call hydrogen ion a proton? Do you remember what a proton is? What's a proton? What's a proton? Someone tell me.
Positive charge.
It's a positive charge. So proton is a positive charge. It's a positive particle within the atom. If you remember, what is the basic structure of a hydrogen atom? How many protons does it have? How many electrons does it have?
Pretty sure it's 2 protons, 1 electron.
How about we say that it has 1 proton and 1 electron? How would you, with that idea, Miranda, what would be a hydrogen ion that's positively charged? if it has one proton and one electron.
To be honest, I'm not sure.
Well, the only way that we would that we would form a hydrogen ion is if it has one proton and it has one electron. The only way to do that is to take away the electron, right? And that would result in just a positive charge, which in the case of hydrogen is just a proton. Does that make sense?
Yes.
So acids release hydrogen ions or protons. Acids are hydrogen donors. When they give up a proton or a hydrogen ion, they become hydrogen ions and a negatively charged thing because it's kept the electron off from the hydrogen. Anything that has a negative charge will most likely take a hydrogen ion back. This isn't stable by itself right here. The most common acids in the body are hydrochloric acid. Acetic acid is a very common acid. If you think acetic acid is vinegar, vinegar is 4% acetic acid or 3% acetic acid, somewhere in there. Carbonic acid is the blood pH. It's the acid that maintains the blood pH. It's the buffering system of blood. Bases, acids are hydrogen donors. Bases are negatively charged anions, or maybe even not even negatively charged sometimes. But substances that will easily take up hydrogen ions. So acids give them up, hydrogen ions, bases take them up. They accept them. The most common bases are the bicarbonate ion and ammonium or ammonia. So hydrogen ions give up acids give up hydrogen ions, bases take them up, accept them. The pH scale is a measure of the free hydrogen ion concentration in a solution. This scale is logarithmic, where each successive change in a pH unit, so if you go from pH 1 to a pH of 2, you have a 10-fold change. You go from a pH of 1 to a pH of 3, you have a 100-fold change. Go from a pH 1 to a pH of 4, you have a 1,000-fold change. That's what that log means. Here. However, if you see there's a negative there, that means that pH is the inverse of the hydrogen ion concentration. So the greater the hydrogen ion concentration, the lower the pH will be. So the more acidic a substance is, the lower its pH number because of the higher the hydrogen ion concentration. So as the hydrogen, and one other thing, as the hydrogen ion concentration goes down, the concentration of hydroxide is going to increase in a reciprocal fashion. So as the hydrogen ion concentration goes down, the hydroxide ion concentration is going to go up. Things are working in a 10-fold unit here. pH of 1 to pH of 2 is a 10-fold increase in the hydrogen ion concentration. Sorry, is a 10-fold decrease in the hydrogen ion concentration. The higher the number, the lower the hydrogen ion concentration. The higher the pH number, the lower the hydrogen ion, the greater the hydrogen ion concentration. Let me say that again, just so that I make sure that I say it right. The lower the pH number, the higher the hydrogen ion concentration, the more acidic a substance is. The greater the pH number, the lower the hydrogen ion concentration, and the more basic the substance is. Your stomach has a pH of about 1 because there's a lot of hydrochloric acid being secreted into your stomach. I'll let you know just an interesting fact. When you open a can of Coke, the first time you open it, if you check the pH right at that moment, it has a pH of about 1 or 2 also. I had someone tell me that, and of course, being the argumentative little turkey I once was, but I can't say that I'm not still argumentative sometimes. I had to say, no, it's not. And then I went to the lab and tested it, and yes, it has a pH of about 1 or 2. Coffee has a pH of about 5. So it's still fairly acidic. Blood has a pH of 7.4. So it's on the acidic side of neutral. So it's a little acidic. Seawater has a pH of 8.4, so it's more basic. Oven cleaner has a pH of 13.5. And if I remember right, toilet bowl cleaner is fairly basic. Is actually, let me say, not fairly basic, let's say it's really basic. I'll have to measure it at some point. I'll take some out and see what it is. I have some pH paper here in my house. Acids that dissociate completely are very strong, and that dissociation, they give up the hydrogen ions completely. Irreversibly strong. They will not reform. The negatively charged anion here will not easily take the hydrogen ion back, if ever. Acids that dissociate incompletely, they may or may not give up the hydrogen ion, are weak acids. Bases that very easily bind up hydrogen ions and very quickly bind them up are strong bases. Bases that may or may not accept hydrogen ions are weak bases. So strong bases quickly give up their hydrogen ions. So, let me say that again. Weak acids, strong acids easily give up their hydrogen ions. Weak acids may or may not give up their hydrogen ions. Strong bases quickly and easily bind up the hydrogen ions within the solution. Weak bases may or may not bind up the hydrogen ions. Buffers are chemical systems that carefully regulate the homeostasis of an acid-base system. Carefully regulate the pH of a substance. They do this by resisting large changes in the pH, by releasing hydrogen ions if the pH increases, and binding up hydrogen ions if the pH decreases. They are a combination of a weak acid and a weak buffer, or a weak base. So combination of a weak acid and a weak base. So if the pH of a solution starts to become too basic or too alkaline, the buffer will release hydrogen ions into the solution. And therefore lower the pH, making it more acidic. If the pH starts to increase and becomes or the pH starts to decrease and it becomes more acidic, the weak bases will start to bind up the hydrogen ions, bringing the pH, making the solution less acidic. So buffers work to convert strong bases or acids into weak acids or bases by removing or adding protons to maintain the pH within narrow limits. The pH is only the measure of the free hydrogen ion concentration. So if we bind up some of the hydrogen ions, we make the solution more basic. If we free up some hydrogen ions and increase the amount of free hydrogen ions, we make it more acidic. The most common buffer system that we're familiar with in physiology is the carbonic acid bicarbonate buffer system, where we have and the weak acid of carbonic acid and the weak base bicarbonate. This is the primary buffer system of the blood. If the pH of the blood starts to become more basic, this carbonic acid, Paisley, stop. This base will release hydrogen ions and will disassociate and give up hydrogen ions to make the blood more acidic. If the blood becomes more basic, or sorry, if the blood becomes more acidic, this base will start to accept hydrogen ions, which will increase the pH or make it more basic. So carbonic acid acts as a weak acid, giving up hydrogen ions if there's a shortage of hydrogen ions, or if the pH becomes too basic. Bicarbonate isn't actually a isn't actually a really strong base, but it's not an acid. It will act as a weak base by binding up hydrogen ions to, sorry, so it will bind up hydrogen ions to make the solution less acidic, therefore bringing the pH number value up. So these systems are a combination of weak, let me just summarize real quick. These solution buffers are a combination of a weak acid and a weak buffer. If the pH becomes too basic, the acid is going to give up hydrogen ions, making the solution more acidic. If the solution becomes too acidic, the weak base is going to start binding up the hydrogen ions, making the solution more basic. Any questions? Let's take 10 minutes here. I will see you guys back here at 11:05 approximately. I thought I updated this PowerPoint. Yeah, there's a lot. I revised it and I uploaded the revision in this. So I'm like, no, I changed this. I know I changed it last night too. It's not changed. I may not what's wrong. Although, of course, I don't do it to her. I just want to pause one and then stop. I do the same thing that she said to me. I'll just. Just for a second. I can't remember if there's still changes that I didn't like. I made all these, is it bad? Okay. When I made all those changes and it's not coming up, it's just frustrating me. So let me see. All right, well, which one? Do you know where they are? I can show you. It's actually really easy. Oh, I can show you. It's really easy. Mom, Mom, I have a jack in the back of my car.
Mary says she has a jack in the back of her car. It's one of those little. Okay. Depends on if you want a nice winter or a lengthy one.
It's a nice one. I've used it.
I don't have anything that I know of. Mary, do you have anything to take the nuts off?
I think there's one in the back of my car. I've used it to pull them off.
Who said,
Joe will be really impressed. I've replaced a flat in my car.
Mary says she's replaced the flat in the car, whether it would work on my car. You don't know. Wonderful. Thank you so much. So the emergency brake is set. Since I haven't moved the car. All right, thank you, Joe. All right, so I keep waiting for him to come, so I'm doing nothing because he's coming. He's been and gone and he's on his way back from York now.
I mean, I've used what I have in the back of my car to fix a flat tire, so I know it works. For someone that was one of the, probably the second time in my life I've ever replaced a flat. It works.
I've tried to replace a flat before, but I kept dropping them off the jack.
Oh, well, don't
Until
drop.
some guy came along and decided to keep killing myself and do it for me.
That was kind of nice of him, wasn't it?
Yeah, so that was years ago.
Well, I'm going to replace this right now because I can't keep doing this lecture not having that fixed. Because here I make all these changes and fix it up and they're not there anyway. Make it a little easier to work through, and of course I haven't done it. Permanently delete. Yes, because I think that's what I need to do. Oh,
The chicken is really delicious.
good. Delete topic. Permanently delete. My students are probably going to have a connection on me here for a second. Let's see. We'll see what happens. is it not uploading? No, I'm trying to do this right now. It's right there. So it's about system. I'm sorry, I'm back now. I realized as we were going through that PowerPoint, I make adjustments to these PowerPoints. As I lecture and I'm working through this PowerPoint, I'm realizing that, I don't like certain things that I adjusted a little bit. And the PowerPoint that I uploaded last night is not the one we've been using. And it's kind of slow torture for me when I realize I made a bunch of changes, and it does take time to make those changes. And then I come in and it's the original PowerPoint, and it's not the one that I made the changes on. And I make the changes because I think it's better and it's smoother and it's easier to understand. And then, of course, when it's not the changes I made, that just makes me a little crazy. So I'm going to see if this is the one that I just uploaded on my other computer here. We'll find out here in a second. If it's not, I'll figure out why it's not. Okay, yes, it is. So this is the one that I just made, and I don't know why it didn't go in last night, but now it's gone in. So strong acids dissociate completely and are irreversibly strong. So dissociate completely, and this dissociation is irreversible. Weak acids dissociate incompletely, and the reaction is reversible. Strong bases quickly and irreversibly bind up the hydrogen ions in the solution. Weak bases incompletely and reversibly bind the hydrogen ions. So it's going to start at the very beginning. Let's do that one instead. Are you seeing the PowerPoint?
Yes.
Good. So remember that buffers are combinations of a weak base and a weak acid that maintain the pH by either releasing free ions into the hydrogen ions into the solution or binding them up. And it's a constant balancing act. Stop looking at me. Stop looking at me. A substance that is very acidic that's very acidic may have a pH of 1 or 2. This means that the acidic substance is what? What do you think? If a substance is very acidic and it has a very low pH, what's the answer here? Leo, no, you can't be right there. Someone, if you're not sure, give me a guess.
Is it D?
Is it, say it again?
Is it D, like D as in dog?
Why do you say that, Asante?
Honestly, I'm not sure. I was just taking a guess.
Well, you're right. You're right. So if you remember, a solution that has is very acidic is going to have a high hydrogen ion concentration. And because we know that the pH measurement is actually the inverse of the hydrogen ion concentration. The lower the pH measurement, the higher the hydrogen ion concentration. That's why that D is correct. Stop looking at me. A buffer will release hydrogen ions if the blood pH rises, falls, stays the same, becomes neutral. What do you think the answer is? Why would a buffer release hydrogen ions? Why would it add more to the solution? All right, I know you're all there. Someone give me an answer.
I'm gonna guess B.
Why would you say that?
B, because if I was just guessing, but I'm gonna take another guess and say, like, because if it's becoming more acidic, it's gonna want to balance itself out, if that makes any sense.
Okay, it's kind of right. It actually, the answer is going to be because it rises, because the one thing that you need to remember here is that the pH bear with me here. The pH, any pH measurement is inverse of this. So the greater the hydrogen ion concentration, the lower the pH value. A buffer will add to the hydrogen ion concentration if it becomes if the pH starts increasing, because this hydrogen ion concentration is not enough. So it's going to add to this to lower the pH. Going to add to this to lower the pH. It would, the only reason to give it, to increase the hydrogen ion concentration in a solution is if if the pH is becoming too basic, meaning it's rising. A substance that dissociates into one or more hydrogen ions and one or more anions is what? What's a substance that's going to dissociate into hydrogen ions and something else?
A base?
Not, you're close, but not exactly. If it's going to dissociate, it means it's going to give them up. So let me reword it a different way. A substance that gives up hydrogen ions, one or more hydrogen ions, and the result is one or more anion, is what? It's an acid. Anything that's going to give up hydrogen ions, bases take them. High acids give them up. Something that binds up hydrogen ions is a base. Something that gives up hydrogen ions is an acid. A substance that dissociates into cations and anions, neither of which are a hydrogen ion or a hydroxide ion, is what? Where did we see cations and anions before? Before we even got into this discussion about pH. Someone go back and scroll through and tell me where we saw this before. We saw the definitions before of a cation and an anion. Where did we see them?
Is it salt?
It's a salt. You're right. Good job, Quentin.
Thank you.
So something that's going to dissociate into a positively charged ion, a cation, and a negatively charged ion, an anion, it's a salt. What's a proton acceptor or a hydrogen plus acceptor? Hydrogen ion acceptor.
Would
This
that be a
is just
base?
a guess, but a base, yeah.
It would be, you're right, it would be a base. I think you were both saying it. It would be a base. What's a measure of the pH of the hydrogen ion concentration, as I just gave it away? What's a measure of the hydrogen ion concentration?
Did you just say pH?
I just said pH, yes.
Yeah.
What is a hydrogen ion donor? Something that easily donates hydrogen ions.
Would that be an acid?
It would be an acid, you're right, Isabel. A compound that maintains the pH by converting strong acids or bases into weak ones is what? Mainly just look at the first part of that sentence. A chemical compound that maintains the pH. What did we just talk about a couple seconds ago?
Hello? Yeah. I can meet you at the house.
What about a buffer? Sound about right?
That's a better idea. All right.
So a buffer is a chemical compound that maintains the pH by converting strong acids or bases into weaker ones. Now on to some easier material here. I think this is easier to comprehend, easier to wrap your head around. We have different forms of energy. Energy is defined as a capacity to do work. Any energy is something that allows work to be performed. Energy exists in two forms, with each being able to be transformed into the other. Potential energy is stored energy, an inactive energy that has the potential to do work, but is not presently doing it. Kinetic energy is energy in action. Okay. Where work is being performed by moving objects. So your food or your fat storages in your body are stored energy. Inactive energy that could be used to do work, but is not presently being used for that purpose. Kinetic energy is the burning of fat to make ATP, the universal energy storage for the body. A few different forms of energy. We have that chemical energy, where energy is stored in the form of chemical bonds. The major example of this is that we can break down ATP into ADP, an inorganic phosphate, which releases energy that can be used to do other things. So this is a stored type of energy. ATP is not very stable. And so usually we store it in another form, and then we make that form that we've been storing it in to convert that to ATP that then can be used. So there's no way of storing this anywhere. And so we usually make it fairly quickly, and then we use it immediately. But we store it adipose tissue that can then be broken down to make this. Electrical energy is the movement of charged particles. Electrical currents are generated when charged particles move across a membrane. Talk a lot about this when we talk about the nervous system. So electrical currents are generated similar to a battery. If you think your battery, you've got a battery, it's made by a separation in charge. When we allow for the movement of those particles from one part of the battery to the other part of the battery, that's electrical energy. When they're stored and they're separated, that's a chemical form. It's a potential energy source that can be tapped. And then that's when the movement occurs. And we use that flow of charges across in the battery to do work. Mechanical energy is the energy involved in moving matter. Oh, really, Mary? Bear with me just for a second here. So energy, mechanical energy is where the biceps contracts to move the arm closer to the forearm. Or actually, I think it's the reverse. This is the arm, this is the forearm. Moving the forearm. So the movement is actually the flexion of this joint. If the triceps contracts, it's an extension of the joint. So mechanical energy is any time that there's a movement in the matter. Radiant or electromagnetic energy is energy that travels in waves that can vary in length, including visible light, infrared waves, radio waves, ultraviolet rays, or X-rays. So this is small wavelengths. If you remember, we talked about the microscope and visible light waves and electron wavelengths. Those are all radiant energy. Chemical reactions and chemical equations. So chemical reactions occur whenever chemical bonds are formed, rearranged, or broken. Chemical reactions can be written as chemical equations. Reactants are the substances on the left side of the equation. And they're the substances reacting in the reaction. Products are typically on the right side of the equation. And they're the substances being produced at the end of the chemical reaction. For example, to create methane, we have one carbon atom and we have 4 hydrogen atoms. These are our reactants. They react to form methane, our product. I don't know why that happens. I'm sorry. My thing is really, really touchy. And there's no reason for that. So reactants on the left side, products on the right side. Reactants are what the substance is reacting. Products are the substances being produced. Reversible reactions can go either way under different circumstances. These are symbolized with a double-headed arrow. The reaction can go either way. It can go forward or it can go backward. The law of mass action says, and the direction of the reaction is determined by the relative abundance of either the reactants or the products. Whichever substance is more abundant. So let me put this another way. The direction of the reaction is determined by whether the substances on the right of the arrows are greater or I'm sorry, I don't know what's going on. Give me 1 second here. Whether the substances are, if the substances on the left side of the equation are greater, the reaction is going to go forward. If the substances on the right side of the reaction are greater than the substances on the left, the reaction is going to go backwards. That's the law of mass action. A reaction reaches equilibrium when the ratio of products being formed to reactants being broken down is stable. This reaction is quite common, and we'll discuss it at length here in the future chapters. All reactions are theoretically reversible. So all reactions theoretically could go backwards and forwards. Bonds can be made, they can be broken, and vice versa. If the forward reaction dominates, the product will accumulate. Remember, the product's on the right side of an equation. So if the forward reaction dominates, this product will be accumulate. When neither the forward or the reverse reaction dominates, the reaction is in equilibrium, and therefore there's no net change to either the reactants or the products, both being broken down and made equally. The forward reaction, remember, this is where the product is going to increase, dominates in most biological reactions. So most biological reactions are assumed to be irreversible. These reactions release energy. We call this exergonic. So when going in one direction, it's going to go in one direction and it will not go in the reverse direction. So reactions that release energy are exergonic. If you remember, I think it was last week's lab, we talked about exocytosis and endocytosis. Do you remember that? Somebody say
Kind of.
yes. Okay, thank you. I'm going to erase some stuff here. Let's do this. Clear all drawings. Back up. Clear all drawings. Okay. So some new terminology. Exer, like exocytosis. Exer means to exit. Exiting. Enter, or I think it's enter. Enter. Actually, I think I was right the first time. Enter means to enter. Entering. Gonic means energy. So exergonic means energy that's exiting a reaction, being released from a reaction. This can also be being released. Releasing. Why don't we say that instead? Releasing. Ender means being absorbed, absorbing. So an exergonic reaction, energy is exiting the reaction or it's being released from the reaction. Endergonic means that energy is entering the reaction or it's being absorbed into the reaction. In an exergonic reaction, one of the products is going to be energy that's released. In an endergonic reaction, one of the products is going to store energy. With that in mind, of course, that didn't work. With that in mind, an exergonic reaction is going to release energy. An exergonic reaction, one of the products, this one right here, is going to be energy that's released. The glucose is broken down and requires, the reaction also requires oxygen. The result are the products, energy being released, carbon dioxide and water. Cannibalism are and require energy. These are reactions that require energy, and therefore they're endergonic reactions. Anabolic reactions always are when smaller molecules are being used to synthesize larger molecules. And this synthesis always requires energy. We're going to form bonds. So we've got to have some energy to form bonds. Catabolism produces energy. So these are exergonic reactions where energy is leaving the reaction. One of the products is going to be energy. One of the reactants has to be energy here. Oh, geez. I don't know why that's going on today, and I'm so sorry because I'm going to bring it right back. So exergonic reactions produce energy. So one of the products in this case is going to be energy. In anabolism reactions, one of the reactants has to be energy. I don't know why that keeps happening because I don't know what I'm touching on my mouse is making that happen. So let me come back. So anabolic reactions, the building up of things, and energy has to be invested. Catabolic reactions, the breakdown of things, energy has to be released. The way that I remember this, and it's kind of gruesome, but do you know what cannibalism is?
Yes.
What is it, Quentin?
It's when a species eats their own species.
Yes. So what I like to think of is that's the breaking down of your own species. So cannibalism, catabolism, same thing. Animalism is the opposite. It's the building up. I don't know what I'm doing wrong. I don't know why that keeps occurring. I wish I knew, and I apologize. Because I don't know if it's making you a little sick to watch that happen, because it's making me a little sick. So we have different types of reactions. We have synthesis reactions, which involve that bond formation. If it's going to result in bond formation, then that has to be an endergonic reaction. So it's got to require energy to form bonds. So these are examples of anabolic reactions. This is a basis of, so synthesis reactions are the basis of anabolic reactions. Decomposition reactions are when things are broken down into smaller molecules or atoms. So bigger things are being broken down. This is always an energy releasing process. So this is an exergonic reaction. So these are the basis. Decomposition reactions are the basis for catabolic reactions. Exchange or displacement reactions involve the simultaneous breaking down and synthesis of bonds. So breaking down of bonds and the recreation of bonds, reformation. So parts of the reactant molecules exchange themselves. I think I'm going to learn how to do something different between now and when we have class on Thursday, to do things a little differently here. One other type of reaction that we get are oxidation reduction reactions or redox reactions. These involve these are almost like, let me put it this way. These are like an ionization reaction. Where there's an involved in the exchange of electrons. When we're dealing with things that aren't metals, or we're dealing with organic substances, which we'll talk about here in a few minutes. Organic substances still exchange electrons, but there are hydrogens that accompany it. So it's essentially a movement of an electron with its proton. Because remember how hydrogen atoms are just one proton and one electron. So it's a movement of with the proton also. So if you remember, we talked about the ionization forming an anion from an ion where we give up an electron to another atom. Well, and the other atom that we give it up to gains it. When a molecule in an oxidation reaction, oxidation reduction reaction, the molecules lose electrons and are said to be oxidized. And other molecules in the same reaction gain electrons or hydrogens with them and are said to be reduced. How are you going to remember this? Are you going to remember the oxidation reduction? So there's one mnemonic that I know of. And it is here. Before I give them a mnemonic, let me say this. So oxidation is the gain of electrons or hydrogens, depending on what substance we're talking about. The reduction is the loss of electrons. Or hydrogens. This is essentially, the reaction is an exchange of electrons between the two reactants. So a redox reaction is the exchange of electrons between the reactants. So the mnemonic to remember this is Leo Oscar. What this means is lose electrons, and we can put in here or hydrogens. Is oxidation. Gain electrons or hydrogens is a reduction. So lose electrons is an oxidation. Gain electrons is a reduction. One of the reactants is going to lose electrons. The other reactant is going to gain them. And those are what the products are, is the reactant that lost electrons and the reactant that gained them. So in each reaction, one of the reactants is going to gain electrons and the other one is going to lose them. In this case, copper gains electrons and magnesium loses them and gives them up to copper. This reaction, more organic reaction, there's a loss of hydrogens, it's an oxidation, to bromine, which gains them. Any questions? Guys are being really quiet.
No.
Okay.
No questions.
Okay. Going forward. I'm trying to go forward. So all chemical bonds, gonna do some shifting of gears here. All chemical bonds store energy in the form of potential energy. And all chemical reactions involve either the absorption or release of energy. The fact, with these facts in mind, reactions can be coupled. Reactions can be coupled. My cat is bumping my monitor. Leo, stop, buddy. Reactions can be coupled where the reaction that releases energy is used to drive a reaction that requires energy. So it says 1, 2 here. I'm gonna use 1, 2. I'm gonna switch the numbers here. So reactant 1 turns into product 1 and releases energy in the form of ATP. This ATP is then used to convert reactant 2 here into product 2. Switch the numbers and that makes a lot more sense. One reaction is giving up energy that's being used to drive a reaction that requires energy. Different example, so classifying the reactions, exergonic reactions or oxidation, decomposition reactions, and catabolism. Remember that catabolism and decomposition reactions are both the breaking down of bigger molecules into smaller molecules. Being able to lose electrons requires energy, so that oxidation, Leo goes grr. Lose electrons requires energy. Reduction, anabolic reactions and synthesis reactions are the building up of larger molecules from smaller molecules. This is a reduction. So both anabolic reactions, so the building up requires energy, they're energonic reactions. Reduction reactions are endergonic reactions. So this is when electrons are gained. Remember that Leo goes grr. So gain electrons is a reduction. And the result is a reduced product if a reduction reaction has occurred. And wherever that electron, the reactant that gave up the electron is the oxidized product because it lost the electrons. Factors that influence reaction rates are temperature. If you increase the amount of temperature of a reaction, you're increasing how much energy is available in that reaction. Remember how heat is a form of energy. If you increase the amount of concentration of the reactants in a reaction, you're going to increase how often they react. So you're going to increase the reaction that way. Increase the reaction rate. The smaller the reactants, the quicker they're able to move and collide. And the presence of catalysts such as enzymes and their cofactors or their coenzymes will increase the reaction rates. And these catalysts, when they increase the reaction rate of a reaction, they're an intermediate that increase the reaction but aren't changed by the reaction, which we'll talk about next time. I think it's coming up. Shifting gears a little bit in our last 6 minutes of class. Inorganic versus organic compounds. Inorganic compounds are simple structures that are small sized with few atoms and held together by ionic or covalent bonds. An example is water, sodium chloride, and carbon dioxide. Organic compounds must contain carbon and hydrogen. Write that down. They must contain carbon or hydrogen. Carbon and hydrogen. Organic compounds are usually composed of chains of carbon atoms and also can contain nitrogen, sulfur, phosphate, and oxygen. But they must contain carbon and hydrogen. They're larger in size, they're more complex structures, and they're only held together by covalent bonds. An example are macromolecules and polymers. Remember, polymers are one or more monomers, so one or more subunits covalently bound. So why are these organic compounds carbon-based? Why couldn't it be potassium-based or zinc-based or chlorine-based? Organic chemistry is a chemistry of carbon compounds, and carbon is the basis because carbon, it never loses its electrons. It can never form ionic bonds. It can't lose electrons. It can't gain electrons completely. It can only share them. It's an electroneutral atom. And carbon only has 4 valence electrons. It binds with other atoms so that it can be provided with the 4 more electrons it needs to fill its valence shell. So it only forms covalent bonds because carbon only can share electrons. So there's only covalent bonds in organic chemical molecules. Very versatile, can form large molecules and be formed with very elaborate shapes. So So carbon never loses its electrons, it only shares them. What elements must an organic compound contain? I just said this a few minutes ago. What elements must an organic compound contain?
Hydrogen or carbon.
Yep. So carbon or hydrogen. What types of bonds does carbon form with other bonds?
A covalent bond?
Covalent bonds, right, Genesis? How many bonds is it capable of forming? Carbon. Can only form 4. What type of structures can be made with it? All sorts of structures. Carbon skeletons come in a variety. We can increase the length. We talk carbon skeletons, meaning just carbon and hydrogen. We can have double bonds being formed. We can have branching, carbon skeletons being branched or unbranched. Carbon skeletons may be arranged into rings. If we know that carbon, last thing I'm going to end on here, if we know that carbon is a very electroneutral element, what is a general characteristic of all these carbon skeletons? Are they polar or non-polar?
Non-polar.
Why are they non-polar, Jessica? What do we have to make a polar molecule that we don't have in a carbon hydrogen structure?
Hydrogen or like water.
You're close. The one thing that we don't have is we don't have anything electronegative there. Do you see that? Because carbon is electroneutral and hydrogen is an electronegative. The only thing that we're going to have is non-polar covalent bonds. We can add things, functional groups to it that are going to change that. And that's where we'll start next Tuesday. So we can add things that are going to change that. And I will see you on Tuesday.
All right.
Thank you.
Thank you.
So, what's due tomorrow is the lab 5.
I'm sorry, you're very, I can't understand. Say it again.
The assignment that's due by tomorrow is the lab 5.
The lab 5 and the lab quest.
The lab 5 and lab 5. Okay.
Okay.
So, chapter 2 quiz was already due before the lecture.
I think I extended it out, Lakeisha. Go back and look.
I already completed it, is what I'm saying.
Do you want another chance to take it? Is that what you're saying?
I don't know, because I don't retain like the chemistry portion of A&P fast.
So
So.
you've got it. The only thing that I can tell you is you have to study it. You have to study
Right,
it.
I know. Right. And my other thing is, for as far as the labs, I'm still trying to get into my labs. I've been talking to IT. They put in a ticket for because they have other people that actually specialize in the D2L website,
Yeah.
and I'm waiting for them to contact me. So I just wanted to let you know. But I did get a phone number today to contact them now.
Lakeisha, are you not being able, what is it telling you?
So it's the same thing that the same thing, screenshot that I sent you. Is nothing there but that white page.
I won't remember it because I can tell you how
Okay.
many screenshots I get. What did the screenshot look like?
It was just blank. It wasn't. It was nothing there for me to launch. Normally, it would say launch, so you can go.
Did you call the Wiley phone number?
I called Hack IT, and then they put in a ticket for me with the.
Did you call the Wiley phone number? Or are you just calling Hack IT?
But they did it for me. They put in a ticket for me though for the
They're not in contact with Wiley.
Oh, okay.
That's why I'm telling you, you need to call Wiley. I want to call Hack IT Tech to figure out how a Wiley product works.
Okay. All right then. Thank you.
Do you have their phone number? Wait, Lakeisha, do you have their phone number?
What's the phone number? Let me make sure.
Let me give it to you. 1 second, okay? Give me 1 moment. Their phone number is 1-877 725 7503.
725-7503. Okay, thank you.
My guess, Lakeisha, is that you have a pop-up blocker that is preventing it from loading. But I don't know how to disable pop-up blockers. I just know how to do it when someone else shows me.
Okay.
Okay?
All right. Thanks.
You're welcome. Catherine? You there?
Yeah.
Can I help you with something?
Oh no, I just like to listen to the end and make sure nobody has.
I understand. I understand. Courtney, can I help you with something?
Thank you. Bye.
Okay. Courtney, can I help you with something? Oh, stink. Really? I don't know what is making this.